Hello, welcome to the video. In this lesson, we're looking at section 10.5, where we're going to be looking at angle relationships in circles. So there are different types of line and angle relationships with respect to circles, and there are some theorems that we're going to take a look at that are going to help us be able to either find angles or find arc measures with a specific intersection. So for the first theorem we have is the tangent and intersected chord theorem. So if you have a tangent and a chord intersecting at the same point, which in this case we do, what we can conclude is then the measure of each angle formed is 1/2 the measure of its intersected arc. So for instance, if we're trying to find this angle measure, like angle 1, it is going to be the value of half of this arc measure. So looking at some example problems using this theorem, it says here, it says find line, it says line M is tangent to the circle, find the measure of the angle or arc. So in this particular instance, they want us to find the angle. So angle 1 is going to be equal to half of this arc measure, which is 130 degrees. That means that angle 1 in this particular instance is 65 degrees. Here we have um, an angle that is what, 125 degrees. We need to find, we are looking for arc measure of what, KJL. So in order to figure that out, we're just going to multiply 125 by 2. So that means that uh, arc JKL is going to be 250 degrees. This diagram here shows different spots that two lines that are not parallel, where they could be intersecting with respect to a circle. So they could be, there's three different types of intersections. You could have an intersection that's on the circle. You could have an intersection that's inside the circle, and you have an intersection that is on the outside of the circle. Now, depending on what kind of intersection you have, this is something that could allow us to use different theorems in order to solve some problems with respect to either arc measure or angle measure. So in this particular theorem, this first one is, it says angles inside the circle theorem. So what we have here is a line that intersects inside the circle. If that ever occurs, we can say that the measure of the angle, like in this case, is going to be angle 1 is equal to half of the arc measure of the sums. Looks like it's DC plus AB. And then here looks like measurement of angle 2 is equal to half of the sum, so it looks like AD and BC. Anytime you have something, angles that intersect on the outside of the circle, it appears in this particular one, there are some things that you also have to take into account when they're on the outside of the circle. So here, this first one here, number 1, we'll say, it looks like we have two lines that intersect. One gives you a chord essentially within the circle, so like AB, and C looks like it's tangent. When that's the case, this angle measure is going to be equal to half of the arc measure BC and AC. So it's the difference of that. When we look at two tangents, it looks like it's still the same idea. You're still taking the arc measure here subtracted by the arc measure there. And same thing goes for there. So I guess it really has no variance on where the line is located with respect to tangent or intersecting the circle. It's still going to be half of the difference of the major arc subtracted by the minor arc. All right, so excuse me. So looking at this, we're trying to find the value for x. For example, a, since x is here, x is simply going to be equal to half of the sum of those two arc measures. So it's going to be 156 plus 130. Add those together, times it by 1/2. X is going to be 143 degrees. If we look at B, this is a situation where the intersection's on the outside of the circle. So in this case, X is going to be equal to 1/2 times it by the difference of the major arc subtracted by the minor arc. Again, difference of that times it by 1/2. X is then going to be equal to 51 degrees. This is just illustrating that if you do, again, we do have two lines that intersect on the outside of the circle and are tangent. Those are considered to be circumscribed angles. And with that, we have a circumscribed angles theorem, which states that the measure of a circumscribed angle is equal to 180 degrees minus the measure of the central angle that intercepts the same arc. So what they're saying is this arc A, or this angle, I'm sorry, ADB is going to be equal to 180 degrees minus the measure of ACB. So those things kind of correlate. So with that being said, here they want us to find the value of x. The value of x in this case is part of that circumscribed angle. So I can say that x is going to simply be equal to 180 degrees minus the angle on the inside there, which is 135. X is just going to be equal to 180 minus 135, which gives us 45 degrees. In example B, for instance, it is a little bit different because they're trying. If we originally wanted to find this, but they don't give us that. So what we can say in this instance is that we need to find FGE first. So in order to find FGE, we can look at the arc measure with respect to the 30-degree mark. So you can say that EJF, so this arc measure right here, EJF is going to be simply, hold on. All right, sorry. So we know that arc EJF is going to be half of the arc of EF All right, sorry about that. So EJF is half of the arc of EF due to the measure of an inscribed angles theorem from 10.4. So we can also then make the conclusion that 30 degrees will then be equal to 180 minus whatever this angle is here. And since we don't really know what that angle is, we'll call this Y for right now. So trying to find that angle there, Y, subtracting 180 to both sides. So it's negative 150 is equal to negative Y, so plus plus. So this angle here is 150 degrees. So that means that the angle of EJF, which is X, I'll just put it as X, would then be equal to 1/2 times it by 150, which gets you a value of 75 degrees. And that is being able to look at angle relationships in circles. Hope this helps. Until next time.